problem 101. In this problem, we have a particle which we are releasing it from point A, and it's going to go down over this curve, and finally it's going to enter this area and go up and stop somewhere here. There is no friction between the particle and ground from here to point D, but after that we are going to have friction with the coefficient of mu k. And we are supposed to find the reaction force at point B immediately after starting this curve, and also the reaction force at point C, and also finally we need to find how much it's going to go up to stop. So let's start with the first part. What is the reaction force at point B immediately after starting this curve? To solve that problem, I drew this free body diagram. We have two forces on the body, on that particle. We have gravitational force, and also we have reaction force from the ground, the normal force. And I'm going to use normal tangential coordinate to solve this problem. You can use x, y, or even polar coordinate. All of them are going to give you the same answer. So based on Newton equation, sum of the forces in the normal direction is going to be equal to mass times acceleration in the normal direction. And acceleration in the normal direction is velocity squared divided by radius here, or the radius of curvature. So it's going to be m times velocity squared at point B divided by r. So I need to find the velocity here in order to find the normal force, because the only force we have in the normal direction is nb. So nb is going to be equal to mass times velocity at this point squared divided by r. Now, how can I find the velocity here? You can use work energy equation between point A and point B. Let's put the reference line here. TA plus VA plus U prime from A to B is equal to TB plus VB. At the beginning, there is no velocity, there is no kinetic energy, so this one is equal to 0. Potential energy is going to be mg times 2r, the height. U prime, from here to here, there is no non-conservative force, so U prime is going to be equal to 0 too. And at this point, we have kinetic energy 1/2 of mass times velocity at b squared. And potential energy is going to be 0 because the reference line is here. So from here, velocity squared is going to be velocity at b squared. It's going to be 4 times g times r. And if I put it there, I'm going to be able to find nb. So nb is going to be equal to m times 4gr divided by r. So it's going to be 4 mg. We can do the same thing for point B. At point B, at point C, let's draw the free body diagram. We have gravitational force, and also we have reaction force from the ground. Again, I'm going to use tangential and normal coordinate. At this point, this is going to be my tangential direction, and toward the center is going to be the normal direction. So this is En and this is Et. And we know sum of the forces in the normal direction is equal to mass times velocity at this point squared divided by radius of curvature, which is r. This is acceleration, normal direction, like the previous part. And the only force, we have two forces here in the normal direction. We have NC and minus mg. So this is going to be equal to NC minus mg. So if I know what is the velocity here, then NC is going to be m, that velocity is squared divided by r plus mg. So let's find the velocity here. To find the velocity here, I can again use work energy equation between B and C, or between A and C. Let's do between A and C. Based on work energy equation, TA plus VA plus U prime from A to C is equal to TC plus VC. Again, TA is 0, and there is no non-conservative force except the normal force, which is not doing any work here because it is perpendicular to the direction of the movement all the time. So U prime is 0 too. And VA, like the previous part, is going to be equal to mg times 2r. It is, the height of it is 2r from the reference line. And in the other side, TC is going to be 1/2 of mass times velocity at c squared plus VC, which is going to be mg times height. But it is below the reference line, so it's going to be negative mg times height, which is r. So from here, mass times velocity is mass is going to cancel out, and velocity at c squared is going to be equal to 6 gr. So if I put this in this equation, I'm going to be able to find NC. So NC is going to be equal to mass times velocity at c squared divided by r plus mg. Velocity at c squared is 6gr. If you put it here, NC is going to be 7 mg. So the normal force is going to be 7 times more than the gravitational force. Now, now we need to figure out how much it's going to go up after point D to stop. So it's going to go up from here to here, and finally it's going to stop here. So if we draw the free body diagram here, we have mg, we have normal force, and also we are going to have friction force. And the friction force is equal to mu k times n here, because it is sliding. So this free body diagram belongs to any point after point D. And to find the friction force, which we needed to calculate the work of it, I can use just sum of the forces in that direction is equal to 0. Let's call this direction like y. Sum of the forces in the y direction is going to be equal to 0. And in the y direction, we have normal force and mg times cosine of this angle, which is 30 degrees. So from there, n is going to be equal to mg times cosine of 30 degrees. And the friction force, because it is sliding, is nothing but mu k times n. So it's going to be mg mu k times cosine of 30. Now, we can write, to find the displacement here, we can write work energy equation between any of these points and the final point, point E. Let's do it between A and E. So the work energy equation between point A and E is going to be TA plus VA U prime from A to E is equal to kinetic energy at E plus potential energy at E. There is no kinetic energy at the beginning and also at the end because there is no velocity. The potential energy at the beginning is 2 mgr like previous parts. U prime from A to E is not going to be equal to 0 here. From here to here, there is no work from non-conservative forces, which is just a reaction force. But after this point, the friction force is going to do work. The friction force is going to remain constant all along this. And also, it is always against the motion. So the work of it is going to be the friction force times maximum S, and also it should be negative. So the work is going to be negative F times S max. And the potential energy at the end is not equal to 0 too, because it's gonna end at above the reference line, and the height of it is gonna be S max times sine of this angle, which is 30. So we are gonna have mg times S max times sine of 30, which is 1/2. So in this equation, we have everything except S max, right? We have friction from the previous line, and also we have everything else. So we can find S max from here, the maximum displacement, which is going to be equal to 4R divided by 1 plus mu k times square root of 3.